recording.
Okay, yeah, it usually takes a few seconds, but that was more than a few seconds. Okay, well in that case, I'm glad I waited. Um, okay, so now let's get the screen share going. Okay, so we've seen a few operations that you can perform on matrices, adding them, multiplying them, taking the transpose. Um, Today we're going to see a particularly important one, and that is the multiplicative inverse. So really, it's just the inverse. We refer to it as the inverse of a matrix, which is very useful for describing solutions to systems of equations. So first, before I get into any problems, I'll talk a little bit about the inverse. Okay. So first of all, we were talking about just numbers. You know, every real number has a multiplicative inverse except zero. But when it comes to matrices, first of all, to even talk about an inverse, the matrix has to be square. Otherwise, the inverse is simply, it cannot be defined. And even then, there's still a non-negligible chance that a given n by n matrix might not have an inverse. So in order for a matrix to have an inverse, we have to be able to multiply the matrix A on either side by some matrix B. And that's why it's important that the matrix A be square, so that you can multiply it by something on both sides. So A and B are both going to be n by n. And I should make that clear here. All right. So if you multiply A on either side by B, what you get is the identity matrix. And recall that the identity matrix is, I'll quickly put that in here too. The matrix that has all ones down a diagonal and zeros everywhere else. So I put 1, 1, 1, 1. Okay. And zeros. So this now, actually, what I just typed is a 4x4 case. I'll use dots to signify that this could be a matrix of any size, n by n. And we have the appropriate identity matrix for that size. Okay. All right. So, because since this is the identity element for multiplication of matrices, we would have numbers. The reciprocal of a number x is 1 over x, the number you multiply it with to get a result of 1, the identity for real numbers. So here, it's the inverse of a matrix A is whatever matrix B you can multiply it with on either side. That gives the multiplicative identity element for n by n matrices, the identity matrix. So if there's a matrix B that satisfies this, both of these equations, we call that the inverse. And the way we refer to it is the same as how we can describe a reciprocal of a number using the -1 power, superscript. So inverse might not exist, but if it does exist, the inverse is unique. Okay. So here's some properties of the inverse that relate to systems of linear equations that we've been seeing all semester long. So if a matrix A is invertible, if it has an inverse, then all of these statements are true. And you can say the columns are linearly independent. They span the whole space, Rn. Ax equals 0 means x equals 0. And Ax equals b has a unique solution. So there's none of this case of having an inconsistent system or infinitely many solutions. There's always a unique solution. And this is it. We have a formula for the unique solution of Ax equals b. It's A inverse times b. So if you go to the trouble of getting b inverse, at least now you can solve any such system, regardless of what b is. And to see why, if A has an inverse, I can multiply both sides of this equation on the left by A inverse. So I get A inverse B on the right side. On the left, A inverse times A cancels out and becomes identity. So you're left with just X. All right. Now, there's actually one other property I'm going to put in here. This relates to the transpose that was discussed last time. That if you take the inverse of a transpose of a matrix, that is the same as taking the transpose of the inverse. So it doesn't matter in what order you perform these operations, taking the inverse or taking a transpose, the end result is the same, which is quite convenient. So this results in some rather unusual notation, A to the minus transpose. So this is the inverse transpose or transpose inverse. Again, it doesn't matter. But this is a way to express either one of these matrices in a more concise way. Yeah. So the transpose is the transpose of the inverse. Okay. All right. Now, the inverse is normally not an easy matrix to obtain. I will show you how you can get it. But there's one exception, and that is a case where A is a invertible 2x2 matrix. So if we have a matrix 2x2, A, B, C, D are the entries, and here's this nice formula for the inverse. So this expression here, AD minus BC, that is known as the determinant of the matrix A. So this is what it is in a 2x2 case. We haven't talked about determinants yet in this class, but we will later. It's possible you might have seen them elsewhere. So it's 1 over this determinant, and this has to be non-zero. Of course, for this to be defined, it has to be non-zero in order for the matrix to be invertible. And then over here, look at the pattern of the entries. The diagonal entries, A and D, are swapped. And then the off-diagonal entries, B and C, those are negated. So swap, negate, and then divide by this. And then you have the inverse. I found that this formula for the inverse of a 2x2, I seem to be bringing it up in many different classes that I teach. So not necessarily a linear algebra class. It comes in handy in sometimes in calculus or differential equations or whatever. It's one of these formulas that it's a good idea to honestly to memorize. It's useful that often. All right. Okay. Still not many people here, but oh well. All right. So now we're going to take a look at some problems involving the inverse. Okay. Okay. Okay, so here we have a system of 2 linear equations, 2 unknowns. So this would be described by a 2x2 matrix. So if A is a matrix of coefficients from this system, so if you have a matrix 5, 3, minus 6, minus 3, if you had the inverse of that matrix, then you could just multiply it by this vector, minus 12 and 4, to get the solution of this system of equations. So in this case, you don't have to get the inverse. They've already given it to you. So all you have to, so there's very little to do in this problem. So we define a vector B to be for right-hand side values. So then, to get the so to get the solution, it's, as I mentioned earlier, A inverse times B. So A inverse is given. Now we have B also. So all that's left is to carry out this matrix vector product, and then you're done. You have the solution x1, x2. So I'm going to write out what that is. So here's the inverse matrix and times this vector. So now we carry out matrix vector multiplication. And matrix multiplication is something we've been dealing with lately. So you go across this row and down this column and multiply corresponding elements, and you add. So -1 times -12 plus -1 times 4, and for the first entry, and then for the second entry, you worked with the second row. So 2 times -12 plus 5/3 times 4, and that goes over here. So now you just work all that out, and the solution that you get is 8 and then -52/3. So be wary. Don't just assume that the numbers are always going to work out nicely. And we've seen a lot of these problems in my labs that they often do, but now and then there are exceptions. All right. So in some problems you'd have to actually get the inverse, but once you have it, then it's just multiplying by these right-hand side values, and that's it. Okay. I want to reiterate the other way of doing matrix vector multiplication that you might find preferable to use. Notice what happened here, where the first column, -1 and 2, is multiplied by the first element of -12. And then the second column, -1 and 5/3, is multiplied by the second element of 4. You can see that here. And then we just add that up and get the result this way. Okay. But now here's a problem where now you're just given a matrix A, and the goal is to actually find the inverse. And it's going to be a pain, even for a 3x3. So how we can do this is I'm going to express the unknown inverse in terms of its columns. X1, X2, and X3. So our goal is to find these three, and we can find them independently of each other, just construct a matrix that way. But so then, if I take both sides of this equation and multiply on the left by A, then I'm supposed to get the 3x3 identity matrix. So that's what I've done here. So I'm multiplying the left by A. That's the same as multiplying each column of the inverse on the left by A. And what we get is identity, but here are the three columns of identity. So the vectors E1, E2, E3. Remember, E1 is a vector 1, 0, 0, and this is 0, 1, 0, or 0, 0, 1. So all entries are 0 except one of the entries is equal to 1. Okay. So what we could do is find the inverse one column at a time. Or we could, so that's one way to do it. We can solve each system. AX1 is equal to E1, AX2 is E2, AX3 is E3. But we can also do them simultaneously by, because if we're going to solve these three systems, this one, this one, this one, you're talking about row reducing the same matrix 3 times. But we really would just want to carry out that process once. So I'm going to work with a highly augmented matrix where I have the matrix A, and normally you put a single column to the right to make it an augmented matrix. What I'm going to do instead is I'm just going to put all three of these in here. So what that would look like is here's a matrix A, and then to the right, we put the three columns of identity. Here's E1, E2, E3. So now I can perform row operations on this. And if I were to perform whatever row operations I needed to reduce the left side, that's A, to reduced echelon form, not echelon form, reduced echelon form. Well, anytime you reduce an invertible matrix to reduced echelon form, and I'll make a note of that here. Invertible matrix to reduced echelon form always gives you, as a result, the identity matrix. So if I get reduced echelon over here, it will be identity. And what you'll have over here are the solutions of these systems. AX1 is E1, AX2 is E2, AX3 is E3. In other words, A inverse will appear over here. So that's what you can do. That's one way to get the inverse, is just reducing A to reduce echelon form, but performing the same row operations on the identity. And that will give you the inverse. So let's see what happens. So we're performing row operations based on these entries here. So like I would subtract 5 times the first row from the second. So proceeding like before, like eliminating these entries below the diagonal. And then here, adding twice this row to the third row. Okay, so we start to see entries being filled in over here. Notice that these constants, -5 and 2, actually appeared over here as I'm performing these row operations. Then I move to the second column. So I'm going to take subtract 3 times this row from this row. Okay. And we see the -3 appearing here now. But here we have a problem. All zeros, that cannot happen. So we're not able to get reduced echelon. Well, we can get reduced echelon form, but we're not going to get identity matrix over here. It's just not possible. So at this point, the whole process breaks down. So what we could conclude is that these systems, AX1 is E1, AX2 is E2, AX3 is E3, these systems are inconsistent because we have non-zero values over here and all zeros over here. So whatever systems we'd have to solve to get the columns of A inverse, they're inconsistent. So there is no inverse. Right? So if we had had something non-zero down here, we could have continued and brought this eventually through more row operations over here to get identity here, the inverse here. But sometimes it doesn't work out. You have to be wary of that. So in that problem, the intent was to try to find the entire inverse. But as I mentioned earlier, you can actually find the inverse one column of it at a time, or just find particular columns of the inverse without going to the trouble of getting the whole thing. So that's what this next problem is about. So we have a 3 by 3 again, and we're just going to find one column of the inverse and don't bother with the other two. And then the next problem is the same way. Find the second and third columns. Actually, what I will do is, since what's asked for in this problem is a proper subset of what's asked for in this problem, I'm just going to do this problem. But when I post these notes, I will have this one written out. Okay. All right. So what you can do is whatever columns of the inverse you want to find, second and third in this case, you put those columns of identity in an augmented matrix with A. So now it's a similar process. Repeat, please.
Are we skipping 3?
Yes, I did skip 3, but because they're essentially asking for the same thing. But as I said, when I post these notes, I will have the solution to this included. All right. So what we have here is almost the same as what happened in problem 2, except we don't have a full identity matrix here. We just have a second and third columns of it because the problem is only asking for second and third columns. But how you proceed is the same, but you can perform row reduction on this matrix. Okay, and to solve these systems. Now, I will tell you that, let's see, this case, yeah, the numbers do not work out nicely, as you can imagine from the numbers that we have here. Okay, so for instance here, the first row operation to eliminate this entry, so we're gonna multiply this row by 357 divided by 16, and add that to eliminate this entry right here. Where'd that go? All right. Okay, so that entry is eliminated, but now we start to get some non-integers here, so that was bound to happen. Here we add 100 over 16 times the first row, the third row. To deal with the this entry to eliminate it. But what's interesting is performing that row operation to eliminate this entry also happened to eliminate this one. So what happens is now the matrix is already reduced to echelon form, at least. Not reduced echelon form, just plain echelon form. Now, how you proceed from here, you can either keep going to get reduced echelon form, in which case the columns of the second and third columns of the inverse will appear over here, or you can perform back substitution like I've done in solving other systems. Really, the operations that you're performing are equivalent either way. So what I'm going to do is solve these two systems using back substitution and this echelon form. So I'm going to do the second column first, and then carry out similar operations for the third column. Okay, so for the second column, here are my right-hand side values. 0, 1, 0. Now, what's interesting is these two columns, it seems strange that these were not affected by the row operations I performed. Can anyone tell me why, when I did these two row operations, of course I had a whole lot of change over here. Why is it that nothing changed over here? Oh, and before I need to fix a typo. That should be row 1, not row 2. There's something about the first row that led there to not be changed over here. To zeros. So what I'm doing is I'm taking this whole row, multiplying it by something, and adding it to one of the other rows. But because these elements are 0, whatever I multiply this by and add down here, I'm adding 0. So nothing gets touched over here. All right. Okay. So I'm going to solve the system described by this matrix and this column, 0, 1, 0. Okay. Now, I want the second column of the inverse. So that would be, so this is the element of the inverse from row 3, column 2, row 2, column 2, and then also row 1, column 2. So x12, x22, x32. Notice the second index is always 2 because it's the second column of the inverse. So that's what I'm computing right here from this right-hand side. So for this equation, for a third element, I'm going to have 0 divided by minus 46, so that element will be 0. Then for the second element, I'm working with this row. So I have my right-hand side value minus this element times x32, but that's 0. So I'm left with 1 divided by minus 9.25, and that gives me the second element. And finally, for the first element, I'm working with these entries. So I have my right-hand side value, which is 0, minus 4 times the second element, minus 48 times the third element. I plug those two in here. Okay. Oh. Sorry, I need to fix a mistake here. This element, minus 0.1081, that is x22. That has to go down here. So I need to fill that in. Okay. So this part is 0. This part is 0 because x32 is 0. All that's left is this. Okay. Oh, I see what I did. Okay. Sorry. x22 is this, but it's also this. And that's what I filled in here. So this is minus 4 times minus x22. That's what goes here. And then all that's divided by this element, the minus 16, and we have this here. Let me check the chat. Oh, okay. All right. Any questions about how these 3 entries were found that make up a second column of the inverse? It is the same back substitution process that we've been using. And then it would be carried out again. Third column, we're just working with these different right-hand side values. Other than that, it's exactly the same. So for example, so we're figuring out x33, 23, and 13. So those are the elements, x13, x23, x33. Those are the elements of the third column of the inverse. So here we have a different right-hand side value of 1 over minus 46 to get this element. And then here, notice the same back substitution process being carried out. It's just that we have different elements substituted in here. And then again here. So x2 free and x1 free are substituted in. Okay. So here we have 4 times x23 minus 48 times x33, and that's where the minus 1 over 46 comes in here. All of that divided by minus 16, because that's the entry over here. And this is the result that we get. So then we can finally state what the second and third columns of the inverse are. So here's the second column from all this work, and then the third column from all this work. Generally, I'm not sure if MyLab specified the number of decimal places. I think it might as part of our multiple choice thing, but so here we work with 4 decimal places. When working these problems out, where if a problem asks for a certain number of decimal places, so there's some rounding involved, what I would suggest is, as you're carrying out your work, actually retain more decimal places than what is asked for. Do not round until the very end, because if you round too soon, that can throw your answer off. So then, even if you're carrying out the problem using the right method, then the number that you enter is still wrong, and you don't know why. And that can be extremely frustrating. So keep more decimal places than asked for until the end. All right. So when you're trying to find individual columns of the inverse, really what you're doing is you're solving a system of equations like you have it before, with the matrix A, and then the right-hand side always is the appropriate column of the identity matrix. And once you have that set up, you can proceed exactly as you've been doing in previous sections for solving AX equals B. Okay. Now, this problem calls for what is known as a one-sided inverse. The matrix A here is not even square, so it doesn't have the inverse. I have an inverse in the sense that I defined it earlier. So it's not possible to find a matrix that you can multiply on either side of A and get the identity. But it may be possible to get a one-sided inverse. So I can find a matrix C that I can multiply A with on the left and get the 2 by 2 identity. But then what we'll find is, because of A not being square, that going the other way, A times C, will not give you the identity as well. So we still can't think of it as an inverse. All right. So we want to basically we're trying to solve this equation for a matrix C that's 2 by 3. So what needs to be done is to write out what that actually looks like. So I have this equation in matrix form, but I need to write this out entry by entry. All right. So it says a 2 by 3 matrix C, 2 rows, 3 columns. So that's written out here, times A. Now that has to equal the 2 by 2 identity matrix. So if I write out what this product looks like, I need to multiply these matrices together. So that's what this looks like here. So I take this row times this column. So C11 times 1 plus C12 times 1 plus C13 times 1 gives me this, multiplying this row times the second column gives me this. Notice they're multiplied by 2, 3, and 5. And then similar working with the second row. So this product all worked out. But that has to equal, that has to equal the 2 by 2 identity matrix. One, 0, 0, 1. That's 2 by 2 identity. So what I could do is think of this as a two systems of equations, one for the first column and one for the second column. So I have C11 plus C12 plus C13 equals 1. And then this one, 2C11 plus 3C12 plus 5C13 equals 0. So here I have a system of two equations for the same entries that come from a first row of C. So if I write that out, it's this system here. So this is what I got just from a first row. Then I get a similar system of equations for the second row. What changes? The right-hand side values change because this is first column of, this is the first row of identity, second row of identity. Here I have the same coefficients, but here my unknowns are from the first row of C. Here are my unknowns from the second row of C. So if I go ahead and I'm going to start by solving this system right here. So what's the augmented matrix for this system? We have this matrix right here. Can anyone tell me, how does this relate to the matrix A? Not equal to A, but what is it? Here's A right here. How does this part relate to A? It's the transpose. So these first three columns are the transpose of A. And then here we have a first row of identity right here. So now we can just row reduce this as usual. So we'll take twice the first row, subtract from the second. And what's convenient is now it's already in echelon form. Now the thing is, here we have two rows, three columns in your coefficient matrix. This third variable here, this is a free variable. So we can choose it to be anything and get a solution. But then we need to look at what the problem specifies. It says construct a 2 by 3 matrix C using only 1, -1, and 0. So we have that constraint that if we're going to try substituting something in for a free variable, it has to be one of these values. And you can just try them all and see what happens. But it's worth noticing that if I take these values, 1 and 3, I can see that if I subtract them, I'll get -2. So that's equivalent to saying that this unknown I'll set to -1. And this one I'll set to 1. So that will subtract them. And I get -2. So that gives me these two unknowns. And then and these have to add up to 1. So all three unknowns. But these two cancel out. So that leaves the final unknown that must equal 1. So this is the first row of a matrix C that I'm looking for. The questions about how that was done, it's a little unusual. Sorry, I missed your chat message there. It's supposed to notify me. I'm not sure why it doesn't. Okay. So we do the same thing for the other row, the second row. Almost the same system. So here we have a second row of identity here. But the row operations will be exactly the same because the coefficient matrix is the same. So we quickly get our echelon form. And so now you got to, here again, we have a free variable. So if you want to set these two unknowns equal to plus or minus 1 or 0, one logical choice is to set this unknown to 0, and I set the second unknown equal to 1. So then this equation would be satisfied. So in other words, I said that C23 equal to 0, C22 equal to 1, so that this equation is satisfied. And all of my unknowns have to sum to 0 in this case. So if these are already specified by the second equation, I can fill in this one by making sure that this one cancels out the others. So it becomes minus 1. So now I've solved for both the first and second rows of my matrix C. So this matrix C, if I multiply it on the left with A, I'll get the identity. So it's a left inverse, if you will. So the last thing a problem asks for is, what if I multiply on the right? I can do that. A has 2 columns, and C has 2 rows. So A times C is a well-defined product. But what I get is this, and so it's not even close. So C times A is a 2x2 identity, but A times C is not the 3x3 identity. So there's no way that the matrix A can be made invertible because it's not square. So you know that going in. But here we see that that even if you do find a matrix that from the left gives you identity, it won't do it on the right. The next problem is similar. Again, trying to find a one-side inverse. So a matrix you can multiply on the right with A to get identity. So A is 2 by 4, 2 rows, 4 columns. So D needs to be 4 by 2 to get the 2 by 2 identity. So you can solve for it in the same way as the last problem. So here's a general D, and then you get a system of equations like before. And so if I write out the product A times D, then the first column has to satisfy these equations to get the first column of identity. And then we have this second system for a second column of D to get the second column of identity. Now, in the previous problem, I was solving for the rows of C. Now I'm solving for the columns of D. What's the difference? In the previous problem, I was multiplying A on the left by C. But now I'm multiplying on the right by D. That's why it changes from rows to columns. So if you were to write out the product A times D in the same way that I've done here with the product C times A, and you equate it to the 2x2 identity matrix, that's where these equations come from. All right. Okay. Because here we have, look at the coefficients, 1, 1, 0, minus 1. That's the first row of A. 0, minus 1, 1, 1. Second row of A. So now I can try to solve this system using only 1 and 0 as filling in for values of D. Now, you don't have to go to the trouble of row operations. For one thing, if I were to look at the augmented matrix for this, it's already in echelon form. So no row operation is needed. But here's what you can do. Notice this entry, D31, okay. Oh, actually, I'll work with this one because it's non-zero. D11 only appears in this equation, doesn't appear in this one. Whereas they have D21 and D41 in common. So what I can do is I can set D11 to 1, set V's to 0, and therefore D31 also 0. So so because this expression has to be 0 anyway, I can just set all three of these to 0, and then D11, which is not involved in this equation anyway, just set that to 1. Similar over here, I need this to become 1. D32 is not in this equation, so I can set it to 1, everything else 0. So that is, there are infinitely many solutions, but this is a solution in each case that is using 1s and 0s. So using the fact that certain variables are only involved in certain equations makes it easier to figure out a combination that'll work. Okay. All right, so this is the matrix D that works. So if you multiply it on the right with A, you'll get the identity. Now the question asks, is it possible to find any matrix that you can multiply with A on the left and get identity? And here I explain why it's not possible. So suppose there is such a matrix. I'm going to do proof by contradiction. So C times A is equal to 4 by 4 identity. Now A is 2 by 4. If C is 4 by 2, then the result is 4 by 4. So here's what I can do. I can take this equation, C times A is identity, multiply both sides on the right by D. So matrix multiplication is not commutative, but it is associative, and I can use that to advantage here. So I have C times A times D. So what I could do is I can associate the C and the A together. And by assumption, that's identity. So what am I left with? It's just D. Now, if I use the same starting point, we go associate the other way, C, A, D. I associate A and D. Well, I already know that's identity. So I get C. So C times A times D is equal to D and also C. So based on this assumption, C and D have to be equal. But if I do, now A times D is identity, but if I multiply D with A, and you can work it out, what you find is that you do not get identity. So that's a contradiction. Therefore, this assumption has to be false. So there is no matrix I can multiply A by on B left to get the 4 by 4 identity matrix. So this is a helpful tool for proving things involving matrix multiplication, taking advantage of the fact that matrix multiplication is associative, so I can group these together in any way I want, as long as the order of which matrices are multiplied does not change. You can use whatever grouping to try to obtain your result. Last problem, we have so the word problem. So here's a matrix where each entry is indicating flexibility in terms of inches per pound. So we're describing forces being applied at 3 points by this 3x3 matrix. So if D is a flexibility matrix, then the inverse of D is called a stiffness matrix. So what we're really trying to do is solve a system involving, with right-hand side are deflection values. So we have a deflection of 0.03 inches at 0.3, 0 deflections at the other points. So in other words, the right-hand side is 0, 0, and then 0.03. So the first job is to get the inverse of this flexibility matrix. So here's the augmented matrix we work with, where I augment D with identity. So then the goal is to use row operations to get reduced echelon form over here, which would be identity. Then the inverse will appear over here. Now what I'm going to do for convenience is I'm going to swap rows. I have 0.001 here. It'll be easier to do row operations if I move this row to the top. So I'm going to swap. Whoops. I'm going to swap rows 1 and 3. Then what I'll do is I'll do some scaling to get nicer numbers. So I'm going to multiply the first row by 1,000, second row by 500, and then the third row also by 1,000. That will give me all integers in these entries over here. Well, it'll give me integers throughout. It'll just give me pretty large numbers over here, but that's okay. So now I can perform further row operations using integers. So for example, I can subtract these 2 rows. Looks like I seem to have skipped a row operation. I'll fill in what it would be. So I also say row 3 is equal to itself minus 3 times the first row. So this row operation takes care of this element. This row operation takes care of the element in the third row. So once I've done that, I would have echelon form if I swap the second and third rows. So I'll go ahead and do that. Okay, so now I've swapped those 2 rows. But now I need to keep going to get reduced echelon form. So I need to make these elements equal to 1. So I'm going to scale the second and third rows. So I divide the second row by -4, third row by -2. Now I need to perform further row operations to remove these elements above a diagonal. So like if I take a third row and subtract twice that from a second row and then 3 times that from a third row, I can get rid of all the other entries in the third column. So similar as row operations for eliminating below a diagonal, but now we're eliminating above a diagonal. So now I've taken care of everything in the third column and just performing the same row operations over here. So we're almost done. We just have to take twice twice the second row and subtract it from the third row to get rid of this 2 here. So wait, what happened here? Oh, that should be 0. Okay, so now I have, not only is it reduced echelon form, it's also the identity matrix. And what that means is this matrix over here, that is the inverse. So go ahead and formally state that. That here's D inverse, taken from the last 3 columns of this augmented matrix. So now I can compute the forces that I need. So I multiply D inverse by this vector of deflections, E3. Now E3, remember, that's the vector that has 0, 0, 1. And that's what I want, because I have 0 deflections at the first 2 points, and then there is a non-zero deflection at point number 3. So I have a 1 here times the amount of a deflection, 0.03. So if I write out what that is, so the inverse matrix times this vector, so these are the deflections that are specified. And now I just carry out the matrix vector multiplication. But all that means is I'm just going to take the third column and multiply it by 0.03. And that's the resultant I get. So these are the forces that are needed to produce these deflections. So in general, flexibility times forces equals deflection. But if you turn that relationship around, stiffness times deflection equals forces, using the interpretation of all of these entities. All right. So it is how the answers are required in my labs, that you specify these elements to of this vector. So 0 pounds, minus 7.5 pounds, 15 pounds. All right. So if a matrix is not 2 by 2, then to get the inverse, the way to do it is make an augmented matrix. So your matrix then augmented with identity, and then go all the way to reduced echelon form, and then you'll have identity on the left and the inverse on the right. Yes, it's a pain. And I also promise that I will take that into account when I design test 2, which will not be for some time yet. Okay. So are there any questions about working with these inverses? Okay, I'll continue through this chapter on Monday. I'll stop recording at this point.